All right, so here we have notes on section 2.4, which is on symmetry and even and odd functions. So let's look at types of symmetry first. You can have three types of symmetry. We can say a graph is symmetric about the x-axis, which is what we're looking at here. So if we look at the x-axis here, it's going to look the same. The graph is going to be mirrored across the x-axis. So whatever it's doing on the top, if you flip it down to the bottom, it's a mirror effect. Okay, and symmetry about the y-axis is going to be the same, but about the y-axis. So if we flip from one side to the other, it's mirrored across the y-axis. And then about the origin is going to be kind of both, or I mean, it's about the origin, but if you can reflect it off of one side and then, reflect it about the one axis and then the other one, then it is also considered, it's symmetric about the origin. Or if it's rotated at 180 degrees. Okay, so this probably is a little bit better explanation. The graph can be folded along a line so that the two halves match, and then this one here is rotated 180 degrees. Okay, so the x-axis and y-axis are common lines of symmetry. The origin is a common point of symmetry. So we're going to look at how to test graphs for symmetry, looking at the graph and then looking at it algebraically, and then we'll do some practice here. So the following graphical and algebraic tests can be used to determine if the graph of relation is symmetric to the x-axis, y-axis, and or origin. Okay, so it can be either one or the other, or it can be about the origin. Okay, so if we look at graphically about the x-axis, the way that we look at this is for every point on the graph, we have a mirrored point where the x is the same but the y is opposite. Okay, so if we look at symmetry about the x-axis up here, right, if we look at this point and this point with the same x value, we'll have this y value and then the negative of the same y value. Okay, so that's how we can tell if it's symmetric about the x-axis. And if a graph has symmetry about the x-axis, it's not a function, right? Because you're saying for the same x value, you're going to have two different y values, so it automatically makes it not a function. Okay, and then for every point, for y-axis symmetry, for every point x comma y on the graph, you'll have a matching point that is the negative x with the same y. So if we look at here and here, we have the same y value, but the x's are opposites. So one's going to be the positive version, one's going to be the negative version. And then if we look about the origin, for every point you'll have the opposite x and the opposite y. Okay, so say this point here is 1, 1. We also have the point -1, -1, right? And that's kind of how you tell graphically. It's a lot easier to just see, you can just look at the graph and tell visually if it does have symmetry and what type. This is just kind of explaining in words what you're seeing. And the algebraic test is fairly easy. To find symmetry about the x-axis, you'll replace y with negative y and see if the equation is the same. And I'll show you what that means in some of the example problems. With testing symmetry about the y-axis, you replace x with negative x and see if the equation is the same or not. And then origin, you replace both x and y with the negative x and negative y and see if the equation is the same. So let's kind of jump into these examples because it's a lot easier to see when you're doing the practice. So number one, we want to determine if this has symmetry and what kind. So to test, I don't know why I always start with the y-axis symmetry. We'll just replace the x's with negative x. So I always keep these in parentheses first because it's really important to see what you're doing first. And in this case, you're multiplying by -1 and then you are applying the exponent there. And the even Even exponents will always end up being positive, so this is just going to equal x to the fourth minus 4, and then negative x squared is negative x times negative x, which is just x squared. And we can see here that the equation that we started with is the equation that we ended with. So we do have origin about the y-axis. Okay, and then let's test origin about the x-axis. That's when we switch to negative y. So we have negative y is equal to x to the fourth minus 4x squared. So we want to see, is this equation equal to our original equation? And our original equation is just y equals, so we'll multiply both sides by negative 1 so that we can get y equals again. And then we'll get negative x to the fourth plus 4x squared. So this is not equal to what we started with. So we do not have symmetry about the y-axis. And then you can test for symmetry about the origin by replacing both. So we'll do negative y is equal to negative x to the fourth minus 4 times negative x here squared. Then we get negative y is equal to x to the fourth minus 4x squared. And therefore y is equal to negative x to the fourth plus 4x squared. So we don't have it here. We don't have it here, but we do have it here. So we'll just check the one box there. All right. Number 2, let's replace x with negative x. So we have negative x times y is equal to 6, and that just makes us negative xy is equal to 6. There's no origin there. It's not equal to the original equation. Let's try about the x-axis. We have x times negative y is equal to 6, and we also get negative xy is equal to 6. There is no symmetry there. It's not equal to the original equation. And then we can replace both of them. Negative x times negative y is equal to 6. This is equal to positive xy is equal to 6. This is the same as the original equation, so we do have symmetry about the origin there. Looking at number 3, let's replace with negative x, so 4 times negative x plus 3 squared plus y squared is equal to 16. So then we just kind of have to rearrange this. There's not really a lot we can do here without doing a lot of work, but you can see that this is not going to end up being the same. It's going to change, the same as this. If we do x plus 3 squared and negative x plus 3 squared, it's going to change the signs. So we automatically know that this is not the same equation here without doing anything else. If we change the y's to negative y, we'll have 4 times x plus 3 squared plus negative y squared is equal to 16. Well, this will all stay the same, and we'll just do the operation negative y squared is just positive y squared is equal to 16. And we can see here that this is equal to the original equation, so we do have some origin about the x-axis here. Okay, and then our last test is for about the origin, where we will replace both of them. So we'll have 4 times negative x plus 3 squared plus negative y squared is equal to 16. And if we just do what we can here, which all we can do is square that y, that negative y is going to be positive y squared. We don't have the original equation, so there's no symmetry about the origin. So just x-axis there. Looking at symmetry about the y-axis, we can replace x with negative x, so we have y squared minus, and then in parentheses here, negative x squared is equal to 1. And then that's equal to y squared minus x squared is equal to 1. This is the original equation, so we'll check off this box or x out that box. Then replacing y with negative y, we have negative y squared minus x squared is equal to 1. Negative y squared is the same thing as y squared. So you can see we also have the same equation here. And then looking about the origin, if we do negative y squared minus negative x squared is equal to 1, we also get y squared minus x squared is equal to 1. So we have all three types of symmetry here. And you can double check this on the graphs too. We haven't actually been looking at the graphs, which we probably should take a look at those. So number 5, let's check about the y-axis. So we'll replace x with negative x. Y is equal to the cube root of negative x minus 1. Well, sorry, this is the cube root. So we could pull out a negative from there, and we get negative cube root of x plus 1. Not the same as the original, so no symmetry about the y-axis there. Let's replace y with negative y. It's equal to the cube root of x minus 1. We multiply it here, we get y is equal to negative cube root of x minus 1. Also not the same as the original, so let's check the last one. Negative y is equal to the cube root of negative x minus 1. Negative y is equal to negative cube root of x plus 1. And then if we multiply by 1, it gets rid of that negative. But we have a plus here and a minus here. So it looks close, but it's actually not symmetrical either. So we don't have any types of symmetry here. And we can see here's the origin. There's no types of symmetry there. If we were to look at the x-axis, no symmetry. The y-axis, no symmetry. So it's pretty clear on the graph too that there's no symmetry. Number 6. Okay, let's replace x with negative x. We get y is equal to negative absolute value of negative x is equal to negative 2. And first, let's just never mind. Let's not do that. Okay. And here we have y is equal to, well, if we take the absolute value of a negative x, that's going to just be x. So the absolute value of any negative number is just the positive version of that number. And we see here that we end up with the same equation again. So we have axis about the y, or symmetry about the y-axis. Replacing y with negative y, we get negative y is equal to negative absolute value of x minus 2. We multiply everything by negative 1 to get y. We get y is equal to the absolute value of x plus 2. No symmetry here. And the last check for both, if we do negative y is equal to the negative absolute value of negative x minus 2. Negative y is equal to negative absolute value of positive x minus 2. And then again we get y is equal to the absolute value of x plus 2. Not symmetrical about the origin. And you can see here the only symmetry we have is about the x-axis. It's reflected across that. You can see that pretty clearly. And nothing with the y-axis. I don't know if I said y-axis. I meant y-axis. Nothing about the x-axis or the origin. And let's stop these notes here because I'm going to run out of, well, I'm going to run out of battery.